Thank you very much. Now, you think you've heard about some big things, airplane things. These are some really big things you're about to hear about. These guys like to take really tiny things and then bash them into each other in really big things. That's basically the complete description of the experiment, I believe. Our next speaker, Luis Granado Cardoso, is a controls engineer at the Large Hadron Collider Beauty Experiment. I'm sure you all know what that is, at CERN. People don't like my jokes, I've noticed that. Where they do fundamental physics research and try to find what makes up our world. CERN is a big player in big data, generating huge amounts of data every second. Are they generating it now that you're not there? Probably they still are, yeah. This data is analyzed in global distributed computing systems that are similar to the principles of IoT, and therefore very relevant to our discussions over the last day and a half about big data and what you do with enormous amounts of data that has to be analyzed in real time. With that, I'd like to introduce Luis Granado Cardoso.
Thank you. Thank you for your introduction, Dr. Solly. So, I come from CERN. CERN's official name is Organisation Européenne pour la Recherche Nucléaire. However, Heisenberg thought that the acronym CERN was not very cool, so he decided to keep the name of the previous council created for CERN, which would be Conseil Européen pour la Recherche Nucléaire, CERN. CERN is the largest particle physics laboratory in the world and is home of the largest particle collider in the world, the LHC, Large Hadron Collider. This is the CERN's mission as stated in the Convention for the Establishment of CERN. So basically it says that CERN is an institution dedicated to pure physics fundamental research without military and commercial applications, and all the data that we get at CERN is free and openly available to anyone that wants to analyze it. Of course, we also have some other missions. So to put all this together, we do need to do a lot of technology development, and also as an international organization, we do promote the international collaboration. So at CERN, we have 10,000 researchers belonging to 600 institutes from over 130 countries that come to CERN to do their research in particle physics and engineering, material science, and all these related fields. We also have a big part in training the scientists of tomorrow with programs of PhDs, fellowships, summer students, School of Computing. Every year, thousands of students come to CERN to learn about the new technologies, the new physics, and then they will go on to pursue their career in science and physics, hopefully. Hopefully they get excited with this. So these are some of the CERN achievements over the years. We have discovered a lot of new physics over the years. Maybe the one you know best is this last one in 2012. In Atlas, in the CMS detectors, we found a particle which has the characteristics of the long-thought Higgs boson, so it must be the Higgs. And this gave way to a Nobel Prize to Mr. Peter Higgs and Mr. François Englert for the theorizing of the model of this particle Higgs boson. So what is the LHC? The LHC is a huge particle collider. It's 27 kilometers circumference, or 70 miles. And it can accelerate particles to almost the speed of light, very, very, very near the speed of light. And it does this by using some more than 9,000 superconducting magnets working at cryogenic temperatures of almost absolute zero. This is colder than outer space. And it's able to accelerate particles. In the first run from 2010 to 2013, we accelerated them at 3.5 TeVs per beam. We have two beams, one going each way, for a total energy of 7 TeVs. And now in the second run that we started about 2 months ago, we will be accelerating particles to 6.5 TeV, so the double. 13 TeVs of energy on the particles going around the CERN, the LHC. The LHC is buried under the Switzerland and France. And yeah, along the CERN, we have several experiments, which I will talk in a bit. So what do we do there? We do like kids in the playground, and we smash stuff and see what comes out of it. It's only that we smash very, very small things at very, very high speed. So this is a depiction of the CERN tunnel and the particles. So this is a proton with 3 quarks, which will be accelerated at the speed of light. There's one coming from here, one coming from here, and then we smash them in special machines and check what comes out of it. In this case, if you know physics, we get Z boson that decays into 2 muons. So as I was saying, along the LHC ring, we have several experiments. The 4 biggest ones are the particle detectors: ALICE, ATLAS, CMS, and LHCb. These 2, ATLAS and CMS, are the biggest ones, and these are general purpose detectors. The goal of these detectors is basically to find new physics at the energies that the LHC can provide. We have 2 of them because we need to independently verify the results. So if ATLAS finds something and CMS finds something, we found something. If only one of them does, we didn't find anything. ALICE and LHCb are particular detectors which are specialized in other kinds of physics. ALICE is trying to create a quark-gluon plasma, which is a state of matter that is expected to have existed a fraction of a second after the Big Bang. And LHCb is dedicated to B physics and to find the slight asymmetry between matter and antimatter that we observe today. So these are pictures of the experiments. I tried to find a picture with a person on it so you can see more or less the size of the experiments, because these things are huge. So this is ALICE, this is ATLAS. Currently, all this part is filled with subdetectors. Oh, sorry. This is CMS. There's Waldo. And this is LHCb, which is the smallest of them all. So how does this relate to IoT? So IoT, as you know, relies on a lot of data. And exactly we are a player of big data at CERN. We can gather 1 petabyte of data per second, which we have to select for the interesting events. And at the end, we start 25 petabytes of data per year, which is a lot. Also, basically, a detector is a network of things. So what we have are millions of channels that capture data, and all these channels are connected through a high-speed network, and the data generated by these machines is mined in distributed global computing resources. So here's your data analytics in the cloud. However, there are also some differences. The sensors themselves are not connected between themselves, as in a usual IoT model. And furthermore, the sensors are dumb, so they have no actuators, they don't do anything. They really just gather the data and push it out. And also the data density is quite different because we have huge amounts of data in very, very small amount of time. So we have to throw some data out and analyze it locally. But these devices have no local intelligence. So it gets sent to some very fast electronics so they can get selected afterwards. So we have a lot of lessons that we can learn from the industry, and investigate the possibility of adapting some of the IoT devices with sensors with local intelligence to high energy physics. Maybe this can be feasible in the future if the sensors get low enough price and get radiation tolerant and things like this. Of course, on the controls part of the LHC, we are already moving to an IoT model with smart devices, because this is basically a lot of industry standardized equipment. It's not for physics data, but for the control of the detector. So, CERN and technological advancements. As you know, to make such a thing, we do have to carry out a lot of research and development on multiple disciplines, like material science, because we need materials that are radiation hard and can withstand extreme environments, like very low temperatures or very high temperatures. The cryogenics and superconducting magnets, so we can accelerate the particles almost to the speed of light. Electronics to gather the data, computing to analyze this data, and a whole host of disciplines. Also at CERN, we are an important test bed for industries, and we have partnerships with companies like Intel and Oracle and Siemens that test their systems at CERN to be sure that then they are ready for the industrial environment. Some of the things we developed at CERN, and without which I think we wouldn't be here today talking about IoT. One is the World Wide Web, which was a great boom to the internet industry for sure. The computing grid, so the advancement of the using of distributed global computing farms connected via the internet. And there are also a lot of applications of accelerated technology in the medical field and other fields like computer chip manufacturing. So I have a picture. So this is World Wide Web. We all know and love. This is the computer center at CERN, which is a part of the LHC computing grid, which goes like this. So data from CERN goes all over the world to be computed distributively, and medical facilities. Lastly, I have a video to show you. It's not very long. It summarizes pretty much what I said.
The core mission of CERN is fundamental research. In the pursuit of its ambitious scientific goals, the laboratory drives innovation, develops cutting-edge technologies, and promotes knowledge exchange, with a broader impact on society than you may expect. Take accelerators. The Large Hadron Collider pushes protons to close to the speed of light. Protons of much lower energies can kill tumor cells. This is called hadron therapy. In 2000, a study at CERN resulted in an optimized and innovative accelerator design for hadron therapy. This study has led to the establishment of 2 clinical centers in Europe that use both protons and carbon ions for cancer therapy. CERN is investigating how to adapt one of its smaller accelerators to provide beams of various particles for medical studies. Ultra-high vacuum technology, developed for CERN accelerators, is at the heart of a new generation of highly efficient thermal solar panels. In 2012, Geneva International Airport opted for these panels to cover a surface of 1,200 square meters on the roof of its main terminal building. Protons colliding in the LHC generate hundreds of new particles. These are tracked and identified by complex detectors the size of buildings. Detectors and electronics initially conceived for LHC experiments are being adapted to monitor the radiation exposure of astronauts and to help doctors improve scans for breast cancer. Detector technologies developed at CERN are also providing cutting-edge tools for X-ray diffraction a technique with numerous applications in industrial and scientific laboratories for the development of new materials, for the optimization of production processes, for drug discovery, or forensic analyses. LHC collisions produce a huge amount of data that must be available to thousands of scientists around the world. Sharing scientific data and information is a challenge for collaborative research and can lead to unforeseen outcomes. Back in 1989, computer scientist Tim Berners-Lee invented the World Wide Web at CERN. He wanted to meet the demand for automatic information sharing among scientists around the world. The web has since revolutionized global communications, with broad societal, cultural, and economic impacts. CERN is a hub for knowledge. Knowledge generated within the laboratory is shared with visiting researchers, teachers, and industrial partners who take expertise back to institutes, universities, and companies all over the world. Through training, education, and large-scale collaborations, CERN is propagating a culture of knowledge sharing at the frontiers of science. At CERN, researchers are changing our understanding of fundamental physics and the structure of the universe, and the technologies developed here have changed the world.
Okay. Thank you very much. I hope you liked it.